All right, let's do problem D. A student determines that the value of N in an unknown crystalline hydrate of copper 2 nitrate by preparing 5 milliliters of an aqueous solution of a known mass of the compound and measuring its absorbance at the wavelength determined in part C. However, the student inserts the cuvette into the spectrophotometer without first wiping fingerprints from it. How will this affect the value of N determined in the experiment? Well, it's important to understand how spectrophotometry experiments work. So we have a light source here. Let's just draw a light bulb. It's not actually a light bulb that's used. It's usually like a mercury lamp or something. But we have our light source, and it's emitting photons, basically. And these photons interact with our cuvette here, which looks something like this. And we can draw our water level, our solution level here in red. This is our solution. So what happens is some of the light, when it interacts with the solution, will get absorbed into the solution, while some will pass right through the solution. And this light that passes through the solution will end up in our detector here. So basically, the detector says, okay, I have a given amount of light, and we know the amount of light that was initially emitted by the light source. So the light that's not here in the detector basically must have all been absorbed by the solution. That's what the detector assumes. So if there's a smudge, for instance, like in a fingerprint, let's say there's a smudge here or something, like on this side, and the photons interact with it, they'll get absorbed by both the smudge and the solution. So the light that comes off of it will be less than what would otherwise come off it if there's no smudge. So the detector will say, okay, because there's less light coming towards me, that means the solution must have absorbed more light. So that means the detector, let me change the color, will overestimate amount of light absorbed by solution. So how do we use this to determine our N value? Because we're trying to find NH2O. Well, we can use what's called our measured transmittance, sorry. So measured transmittance we use the symbol T, and it equals I over I naught. So what does that mean? I basically equals the amount of light that exits the cuvette and hits the detector. So light received by detector and I naught is the initial amount of light that essentially the light that comes from the light source. So we can just say initial amount of light, hence the naught. So our initial amount of light is obviously going to stay the same. We're not changing that. But the light received from the detector is going to be less. So that means that T is going to be smaller than normal. Now we can use our absorbance formulas. So we know that absorbance is equal to our molar absorptivity constant times our cuvette length times our concentration. But absorbance is also equal to the negative log of our transmittance. So because of that, if we have a transmittance that's a lower value, just think about this for a second, our absorbance is going to be greater than normal because of the negative. So we have essentially the log of a smaller value, but it's negative, so it's actually going to be greater. So absorbance is measured as higher than normal. So now we can apply this to our other formula. So we can say, let's say AL for large equals, so absorbance large equals ALC. So So we have this formula A large equals epsilon lambda C. So, oh sorry, epsilon length c. This is our path length for L. So we can now find out. So now we can use this to relate to our other formula. So we know that our absorbance is larger than normal. So let's write A with a subscript L, just to remember that it's larger than normal. And we can set it equal to epsilon path length and then our concentration. So these two don't change. We have our molar absorptivity constant, which is a constant, and our path length, which is always 1 centimeter because of the cuvette length. Now, if we want to find the concentration, we can divide, essentially, Now, if we want to determine how the concentration is affected, so now, how do we relate this to our other formula? Well, we know that our absorbance is higher than normal, so we can write it as A with the subscript L. So we can set this equal to our epsilon path length times our concentration. So these two will stay constant. So it means that to make this absorption value larger, our concentration must have at least been measured as being higher than normal. So we can say concentration is overestimated. So keep this in mind. So how do we relate this to determine how our N of H2O is affected? Well, we can use the simple aspect of molar mass. So molar mass is equal to mass over moles, obviously. Atomic mass over moles. Mass in grams over moles, specifically. So basically, if we have a larger concentration, that means the amount of moles we have per solvent, basically moles per volume, or moles per shit. Okay, so now that we have this formula, now that we know that our absorbance is measured as greater than normal, or greater than the actual value, how do we relate this to our other formula to find our N of H2O? Well, we can say that A with the subscript L to show that it's large equals epsilon path length times concentration. So these two values, our path length and our epsilon, are both constant. So the only thing that must increase is our concentration. So that means concentration is larger than normal. So how do we use this to find how our N of H2O is affected? Well, we can determine the amount of moles, or at least estimate, we can give a characteristic to the amount of moles by saying that our molarity is equal to moles over our volume. Or moles per liter, more specifically. So because we have a specific amount of water that we added, which is 5 milliliters, this number doesn't change. And because our concentration is larger than normal, it means the amount of moles that we have of our compound must also be larger than normal. So we have more, we have basically an overestimated amount of salt. So that means we have more moles of CuNO3 to NH2O. What this means is that we can now determine from molar mass if our amount of H2O is higher or lower than what it actually should be. So remember, molar mass is nothing but mass, your total mass over the amount of moles. So because of that, because our amount of moles is greater than what it normally is, and I'll make this a different number or a different letter just to not confuse it with molarity. It means that our total molar mass is less than what it should be, because we have a larger number on the denominator. Now, from this, we already know what our mass of copper NO3 2 is. That we can just find from the periodic table. The only thing that's not determined is the amount of water that's in solution. Thus, because this is essentially... Thus, because we know what this number is, and because we know that the total molar mass is less than what it should be, our N value of waters is actually going to be lower than normal. So N equals less than what it should be. Alright, now let's try problem E. An alternative method for determining the degree of hydration of copper nitrate is to allow a known mass of compound to react with excess Ki solution, which produces a yellow-brown suspension. Write a balanced net ionic equation for this reaction. So there's one important thing to note here, and that is we have excess... There's one important thing to note here, and it's that we have excess potassium iodide solution, which will come important later when we solve this. So let's start off by writing our main reactions. So we have our copper nitrate, copper 2 nitrate, and it will dissociate into copper 2 plus and our nitrate anion. And then next we also have our potassium iodide dissociating into our potassium cation and our iodide anion. So next, what do we do from here? Well, we notice that we have both spectator ions and reactive ions, which we have to identify. The potassium and the nitrate won't further react, so all we have left is the copper and the iodide. So we have copper 2 plus and iodine minus. Now, we can't just add these two because our final product needs to be copper iodide. So where do we go from here? Well, we need to do a bit of redox here. Our first step would actually be to reduce our copper. So we have copper 2 plus, and we add an electron to form copper plus. And now we need to oxidize our iodine. And because we need 2 iodines to match up with the 2 plus charge of the copper, we need to represent it as 2 iodines. And this will form iodine gas, I2. So now where do we go from here? Well, now we can combine these two equations. We're going to use 2 copper 2 plus, again, to match up with the stoichiometry. And then here's our 2I minus. And that will go to our 2 copper plus, which is from our initial reduction reaction, and our iodine gas. Now, once we're here, we got to remember that the charges need to match up. So if we have 2 copper 2 plus, it has a 2 plus charge, so it'll sort of have 4, if you will, as our number. So we actually need 4 iodine, because iodine only has 1 as its magnitude of charge. So this will then form two copper iodide, which is a solid, and our iodine gas. But that isn't our final answer. We notice that we have an excess of iodine in solution, excess Ki in solution. So what will this do? Well, we already have our iodine gas, and it will react further with more I- to form the I3 anion. So now when we update our final solution, it should look like 2 copper 2 plus 5 I- because we added that extra I- goes to our 2 copper iodine solid plus our I3-. And that's our final answer. Alright, let's solve problem F. The experiment in part E is carried out with 0.1000 grams of the hydrated copper 2 nitrate. To the resulting mixture is added 0.0250 molarity solution of sodium thiosulfate until the color of the mixture has just dissipated, leaving a milky white suspension. This requires 17.20 milliliters of added sodium thiosulfate solution. What is the value of N for copper nitrate and H2O? So this is a titration problem, so we can use given ratios to find out the amount of hydration or amount of water molecules we have. So the first thing to note is what happens when sodium thiosulfate comes into contact with our previous copper and iodine solution. Well, the balanced chemical equation looks something like this. So what we notice here is that when two moles of sodium thiosulfate, or the thiosulfate reacts, it'll react with 1 mole of our iodine, of our I3 ion. So what does this mean? Well, in our initial reaction up here, we notice that we have 2 copper ions reacting, and it produces 1 I3 ion. So it means that because they both have the same 2-to-1 ratio, there's a 1-to-1 ratio between the copper copper 2 plus and the sodium thiosulfate, which is very, very useful. So we can use that. So our first step is to find the amount of moles that we have added of the thiosulfate. So how do we start that? Well, they give us the molarity of the solution, which is 0.0250 molarity, and they give us the volume added, which is 17.20 milliliters, which we can turn into liters to get 0.01720 liters. So how do we find the amount of moles? Well, remember that molarity is just equal to N over V, so molarity times volume equals moles. So we can just multiply these two numbers to get the amount of moles. And we get 4.30 times 10 to the negative 4 moles of our thiosulfate. So that means, because we have that 1-to-1 ratio we explained earlier, we actually have this many moles of our copper 2 plus. So our next step is from this, we can actually find the mass of the anhydrous copper. Remember, the 0.1 grams is of the hydrated copper nitrate. So how do we find the mass of our anhydrous copper? Well, we can multiply it by the atomic mass of the copper nitrate. So we have our 4.30 times 10 to the negative 4 moles, and we have, if we go back to our periodic table, copper is 63.55 plus our nitrate ion, which is our nitrogen, 14.01, plus our 3 oxygen, which should be 48. And this is going to be times 2 because it's our CuNO3 and we should get a total molar mass of 187.57 grams per mole. And if we multiply this times our amount of moles, we will get 0.0807 grams of our copper nitrate salt. But that's just the anhydrous copper. We have to subtract that amount to find the actual mass of water. So if we do 0.1, which is our initial mass of the hydrated, minus the mass of our anhydrous, we'll get 0.0193 grams of water. But now we have to convert this into moles, because this is we're trying to find the ratios. Remember, in the initial problem, it's given 1 mole of copper nitrate, and we're trying to find how many moles of water. So if we divide this by the molar mass of water, which is 18.02, we will get 1.07 times 10 to the negative 3 moles of water. But that's just the actual amount of moles of water. So to find the moles of the ratio, the specific ratio, we need to divide the moles of water by our moles of copper. Remember, they're in a specific ratio. And we get 2.50 moles of water. So that means that N equals 2.50.